Hi again, everyone. Tom McNamara back for our course in college algebra. We have been working on polynomials, and I wanted to show some additional examples where we tackle a couple questions from my math lab just to give you a flavor for how those go. So remember, when we're working with polynomials, there are three key things to look for. The end behavior of the polynomial, which is influenced by the degree and the sign of the lead coefficient. The zeros / x-intercepts / factors of the polynomial, and the multiplicity of the zeros. So if you know all that stuff, you can put everything together and get the graph. And conversely, if you have the graph, like we have right here, you can work backwards and get information about the polynomial. Okay, so we see here, this polynomial, we're looking at the end behavior. That looks like an even degree polynomial with a negative lead coefficient, because it opens down. It's got zeros at -8, -2, and +2, because I can tell the zeros by looking at the x-intercepts of the graph. Okay, it looks like this guy has even multiplicity because it touches the x-axis there without crossing. Let's go back to the question here. Okay, determine the number of turning points and estimate the x-intercepts. Okay, haven't really discussed this idea. Hopefully it's obvious. There are 1, 2, 3 turning points. A turning point involves a turn, right? Mathematicians are not creative with names. So we can see here the graph is rising and then it starts to drop. So there's a turn right there. There's a turning point. There's a turning point right here. There's a turning point right there. Okay, so let's go and start doing some answering here. How many turning points? We just saw it has 3. Check answer. Great, got it. The x-intercepts are, now, it likes us to type ordered pairs. And technically, that's the way you need to do it, okay? The x-intercept of a graph is a point on the graph. So a lot of times we might get a little sloppy and say the x-intercepts are -8, -2, and 2. In fact, I think I just did that. But really, the x-intercept is -8, 0. -2, 0, and 2, 0. Okay, so I'll just be typing these in here. -8, 0. -2, 0. And finally, 2, 0. Okay, check answer. We got them. Wonderful. Okay. State whether A is positive or A is negative. Now, when you're looking at a problem like this, A is the lead coefficient, right? Think about what we already know, okay? We know a lot about quadratic polynomials. And quadratic polynomials look like ax squared plus bx plus c. A is the lead coefficient. So with higher degree polynomials, we just generalize that. We use A for the lead coefficient. And I believe we decided A had to be negative because of the end behavior. It's opening down like that. Down on both sides means that you have an even degree polynomial with a negative lead coefficient. And this here says determine the minimum degree. Now we know based on the end behavior that our polynomial has even degree. But let's think about this here. If I had a quadratic polynomial, I have a maximum of 2 x-intercepts. So this cannot be a quadratic polynomial because it's got 3. Now it can't be a degree 3 polynomial because we just said the degree has to be even. Okay? So the minimum degree has to be 4. Okay? This is a zero of multiplicity 2. So if you add up the zeros with multiplicity, then you can get your degree there. Okay, great. Wonderful. So these examples, very similar. You can tackle them the exact same way as I just showed you. Okay. Let's look at one more here where it gives us this list and we pick the graph. Okay, so I'm looking at this right here. tell you what, the title card can go away, and I'm gonna move up. Okay. So it says identify the graph. Okay, x cubed plus 12x squared plus 21x. That's my polynomial. It wants me to pick the graph. Okay, so I know that I have a odd degree positive lead coefficient, so that should be going up on the right side and down on the left side. Okay? So we can kind of do a lot of narrowing down here, right? This is odd degree but negative lead. This is odd degree, but look at how many zeros it has, right? Look at all the zeros. 1, 2, and even multiplicity 0 there. And 1, 2, 3, 4 zeros. And my polynomial is degree 3. Okay, so this cannot possibly be the graph, because a degree 3 polynomial can have at most 3 x-intercepts. So I'm going to make an educated guess and say this is graph B. Wonderful, got the right answer. Identify the turning points. Okay, since we have figured out this is our graph, we can get the turning points really easy. We just need to look at the picture, right? I got a turning point here at 7, oh gosh, 7, 98, and another turning, at negative 7, 98, and another turning point here at negative 1, negative 10. Okay, let me get those in there before I forget what they are. The turning points are negative 7, 98, and negative 1, negative 10. Okay, great. The x-intercepts. Okay, once again, if we have the graph, this is an easy question. It says estimate, right? Okay, estimate the x-intercept. Type an integer or a decimal rounded to 1 decimal place as needed. Okay, great. Okay, so this looks like negative 10, negative 2, and 0. Let me try that. Remembering that we have to enter both coordinates of our x-intercept. Did it take it? Okay, it took that. It allowed me to estimate. Estimate any local minima. Okay, this is going back to some material that we discussed in a previous section on extrema. Local max, local min. Okay? Notice they correspond to your turning points that we put in before. Okay, so local min was negative 1, negative 10. What? Estimate any local minima. Okay, I'm not sure why it's not taking that answer. It just wants the y value. Okay. Didn't say the coordinates. Okay, there was a local max at 98. Great. No absolute min and no absolute max. Okay, let me tell you why I'm saying no absolute min, no absolute max, right? This right here, negative 10, is a local min, but we can see down here the graph actually gets lower than negative 10. So it is not an absolute min. Remember, absolute min would be lowest value on the graph anywhere. That is a local min, not an absolute min. Same thing with the max. This graph has a local max, but no absolute max. Okay, so we're just putting together the materials that we talked about in the last video. If you know the degree and you know the lead coefficient, you got the end behavior. Okay, you can also figure out some stuff about the x-intercepts and how the graph behaves near 0, right? So for example, this one, D, right? Look at that. Degree 4, positive lead coefficient. Even degree, positive lead coefficient. The only graph that has the right end behavior is this one right here. The rest of them, no, they don't fit the criteria. Okay? So, if you remember those principles that we've discussed in the previous videos, how to find the end behavior using the degree and the lead coefficient, how to find the zeros, factors, / x-intercepts, and how multiplicity of a zero affects the behavior of a graph, you can basically handle any question I can throw at you regarding polynomials.